What if everything you thought you knew about reality was wrong? What if the stars above you, the ground beneath your feet, and the very thoughts firing inside your brain were all secretly connected by invisible threads that defy every law of physics you learned in school? This is not science fiction, and it is not mysticism dressed up in lab coats. This is quantum entanglement, and it is one of the most experimentally verified, peer-reviewed, Nobel Prize-winning phenomena in the history of modern physics, and yet it remains so deeply strange, so fundamentally unsettling, that even Albert Einstein himself refused to believe it was real, dismissing it as spooky action at a distance, and spending the final decades of his life trying to prove it was nothing more than an illusion. He failed. The experiments have been done. The data is in. The invisible threads are real. And they do not just connect tiny subatomic particles in a laboratory. They may, according to the most cutting-edge theoretical physics of our era, stitch together the very fabric of space and time itself, forming the hidden architecture of the entire universe. So let us pull on one of those threads and see where it takes us. Because what unravels is a story that will change the way you understand reality, consciousness, distance, information, and what it means to exist in a cosmos that is far more interconnected than anyone ever dared to imagine. To understand why quantum entanglement is so shocking, you first have to understand what physicists expected to find when they started probing the subatomic world in the early 20th century. The prevailing worldview, shaped by centuries of classical mechanics from Isaac Newton through James Clerk Maxwell, was built on a simple and intuitive foundation. Objects have definite properties whether or not anyone is looking at them, and no influence can travel faster than the speed of light, which Einstein's own special theory of relativity, published in 1905, had established at approximately 186,282 miles per second. These two principles, that reality is objective and that causality is local, form the bedrock of what physicists call local realism. Local realism says that a baseball has a definite position and velocity, even when nobody is watching it, and that if you do something to a baseball in New York, it cannot instantaneously affect a baseball in Los Angeles. You would have to send some signal, a radio wave, a light pulse, a thrown rock, and that signal would take time to travel. This is common sense. This is how the macroscopic world works. And for a long time, physicists assumed it was how everything worked, all the way down to the smallest scales of nature. Then quantum mechanics arrived and began systematically demolishing those assumptions. In the quantum world, particles do not have definite properties until they are measured. An electron does not have a definite spin direction, up or down, until someone performs an experiment to check. Before measurement, it exists in what physicists call a superposition, a strange limbo state where it is, in a very real mathematical sense, both up and down simultaneously. This is not a statement about our ignorance. It is not that the electron has a spin, and we just do not know what it is yet. According to the standard interpretation of quantum mechanics, the Copenhagen interpretation developed primarily by the Danish physicist Niels Bohr and the German physicist Werner Heisenberg in the late 1920s. The spin literally does not exist as a definite value until the act of measurement forces it to choose. The measurement itself brings the property into existence. This was already bizarre enough. But then physicists discovered something even stranger: entanglement. Here is how it works. You can prepare two particles, say two photons, which are particles of light, in a special correlated state using certain physical processes, such as spontaneous parametric downconversion, where a single photon passes through a special crystal and splits into two daughter photons that emerge with their properties linked. These two photons are now entangled. What that means is that their quantum states are described by a single shared mathematical object called a wave function, and the properties of one photon are fundamentally correlated with the properties of the other. For example, if you measure the polarization of photon A and find that it is vertically polarized, then you instantly know, with absolute certainty, with 100% reliability, that photon B is horizontally polarized or vice versa, depending on how the entanglement was set up. And here is the truly mind-bending part. This correlation holds regardless of how far apart the two photons are. You could send photon A to a laboratory in Boston and photon be to a laboratory in San Francisco. You could send one to the surface of the moon and keep the other on Earth. You could, in principle, send one to the edge of the observable universe, 46 billion light-years away, and the correlation would still hold. The moment you measure photon A and find it in a particular state, photon B is instantaneously found to be in the corresponding state, no matter the distance, with no signal traveling between them, with no time delay, with no physical mechanism that anyone can detect connecting them across the void. Now, if you are thinking that this sounds like it could be explained simply, maybe the photons were just assigned their properties at the moment of creation, like two gloves packed into separate boxes, one left and one right, and shipped to different cities, then you are thinking exactly the way Einstein thought. And you would be wrong, for the same reason Einstein was wrong. And proving that this simpler explanation fails is one of the most important achievements in the entire history of physics. But let us not get ahead of ourselves. Let us follow the historical thread. Because the story of how humanity came to accept this deeply counterintuitive truth is itself a riveting drama involving some of the greatest minds of the 20th century locked in a philosophical battle that took decades to resolve. Einstein was troubled by quantum mechanics almost from the moment it was formulated. As early as 1926, in a letter to the German physicist Max Born, who had proposed the probabilistic interpretation of the wave function, Einstein wrote, "Quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he does not play dice." This famous declaration, "God does not play dice," became Einstein's rallying cry against the randomness at the heart of quantum theory. For Einstein, the universe was fundamentally deterministic. Every event had a cause. Every measurement had a pre-existing answer. And the apparent randomness of quantum mechanics was simply a sign that the theory was incomplete, that there were hidden variables lurking beneath the surface, as yet undiscovered pieces of information that, once found, would restore the orderly, predictable universe he believed in. Einstein did not simply complain from the sidelines. In 1935, he mounted his most sophisticated attack on quantum mechanics in collaboration with two younger physicists, Boris Podolsky and Nathan Rosen. Together, they published a paper in the journal Physical Review titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" This paper, now universally known as the EPR paper after the initials of its three authors, has been cited over 28,000 times and remains one of the most influential physics papers ever written. The EPR argument was elegant and devastating, or so it seemed at the time. Einstein, Podolsky, and Rosen constructed a thought experiment involving two particles that had interacted and then flown apart to great distances. They showed that according to quantum mechanics, measuring a property of particle A would instantly determine the corresponding property of particle B, no matter how far apart they were. They then presented a logical dilemma. Either the measurement of particle A somehow instantaneously influenced particle B across any distance, which would violate the principle of locality that Einstein held sacred, or particle B already possessed a definite value for that property before anyone measured it, which would mean that quantum mechanics was incomplete because it failed to describe that pre-existing value. Einstein and his collaborators concluded the latter. Quantum mechanics must be incomplete. There must be hidden variables, additional information not captured by the quantum mechanical wave function that predetermine the outcomes of measurements. The spooky action at a distance that quantum mechanics seemed to imply was, in Einstein's view, not real. It was an artifact of an incomplete theory. Niels Bohr responded almost immediately, publishing his own paper with the identical title in the same journal. Bohr's response was characteristically subtle and philosophically dense. He argued that EPR's reasoning was flawed because it assumed that the properties of quantum particles had definite values independent of how they were measured. According to Bohr's Copenhagen interpretation, you cannot meaningfully talk about the polarization of a photon until you have actually measured it, and the way you choose to measure it, what angle you set your polarizer to, for example, is an inseparable part of the phenomenon. There is no reality behind the measurement waiting to be revealed. The measurement and the result are a package deal. Bohr was not saying that measurement creates reality in some mystical sense, but rather that the question, what is the polarization of this photon, has no answer until a specific experimental context is established. To ask what the photon's polarization is really, in the absence of a measurement, is, in Bohr's view, like asking what is north of the North Pole. The question is grammatically well-formed but physically meaningless. This philosophical standoff between Einstein and Bohr, between local realism and the Copenhagen interpretation, became one of the great intellectual rivalries of the 20th century. They debated at conference after conference, most famously at the Solvay conferences of 1927 and 1930, where Einstein would present increasingly clever thought experiments designed to expose contradictions in quantum mechanics, and Bohr would stay up all night working out why each one failed. Each time, Bohr prevailed, but Einstein was never truly satisfied. He went to his grave in 1955 believing that quantum mechanics, while practically useful, was fundamentally incomplete, and that the spooky action of entanglement would eventually be explained away by the discovery of hidden variables. Meanwhile, Erwin Schrödinger, one of the founding architects of quantum mechanics and the inventor of its central equation, was also deeply unsettled by entanglement. In fact, it was Schrödinger who coined the very term entanglement, using the German word verschränkung, in a 1935 paper written in direct response to the EPR argument. Schrödinger called entanglement not one but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. He recognized that this phenomenon was not a minor curiosity or an edge case, but the defining feature of the quantum world, the thing that made it fundamentally different from everything that came before. He acknowledged that entanglement forced humanity to dismiss the idea of a real physical world in which objects can be identified and localized, and admitted that this was sinister and disturbing. Yet unlike Einstein, Schrödinger accepted that this was what nature was telling us. However uncomfortable the message, for nearly 3 decades after the EPR paper, the debate remained purely philosophical. There seemed to be no way to experimentally distinguish between Einstein's hidden variable theory and the standard quantum mechanical account. Both predicted the same correlations between entangled particles. So how could you tell whether those correlations were pre-existing, as Einstein argued, or created at the moment of measurement, as Bohr insisted? The answer came in 1964 from an unexpected source, a quiet, unassuming physicist from Northern Ireland named John Stuart Bell, who was working at CERN, the European Organization for Nuclear Research in Geneva, Switzerland. Bell was sympathetic to Einstein's position and was actually trying to find a way to make hidden variable theories work when he stumbled upon something remarkable. He discovered a mathematical inequality, now called Bell's inequality or Bell's theorem, that draws a clear, testable line between the two worldviews. Bell showed that if Einstein was right, if particles carry hidden variables that predetermine measurement outcomes and no influence travels faster than light, then the statistical correlations between measurements on entangled particles must obey a certain mathematical limit. But if quantum mechanics was right, those correlations could exceed that limit. In other words, Bell transformed a philosophical debate into an experimental question. For the first time, you could actually go into a laboratory and test whether Einstein or Bohr was correct. Bell published his result in a relatively obscure journal called Physics Physique Physica, and it took several years for the experimental community to catch up with the theory. The first serious experimental test was performed by John Clauser and Stuart Friedman at the University of California, Berkeley in 1972. Clauser, who had read Bell's paper as a graduate student and been captivated by it, built an apparatus to measure the polarizations of entangled photons emitted by excited calcium atoms. The results were clear. Bell's inequality was violated, just as quantum mechanics predicted. The correlations between the entangled photons were stronger than any local hidden variable theory could explain. However, the experiment had loopholes, technical limitations that, in principle, could allow a clever hidden variable theory to sneak through. The most important was the locality loophole in Clauser's experiment. The measurement settings on the two detectors were fixed in advance. So it was conceivable that some unknown signal could travel between the detectors at the speed of light and influence the outcome. To close this loophole, you would need to change the measurement settings randomly and quickly enough that no signal could travel from one detector to the other before both measurements were complete. This is exactly what Alain Aspect accomplished in his landmark experiments at the University of Paris-South in Orsay, France, in 1981 and 1982. Aspect's team introduced rapid switching of the polarizer settings while the photons were in flight, using acousto-optical switches that could redirect photons to different analyzers in about 10 nanoseconds. With the detectors placed about 12 meters apart, light would take roughly 40 nanoseconds to travel between them, meaning the switching was fast enough to ensure that no information could pass from one detector to the other at or below the speed of light during the measurement. The results were dramatic. Bell's inequality was violated by 5 standard deviations, an overwhelming statistical margin. The experimental data matched the quantum mechanical predictions with extraordinary precision and were flatly incompatible with any local hidden variable theory. Aspect's experiment was a watershed moment. It did not quite close every conceivable loophole. For example, the random number generators used to select measurement settings might themselves be correlated in some deeply hidden way, but it convinced the vast majority of physicists that Einstein's dream of local realism was dead. Over the following decades, experimenters continued to close remaining loopholes with increasingly sophisticated apparatus. In 2015, a team led by Ronald Hansen at Delft University of Technology in the Netherlands performed what many consider the first loophole-free Bell test. Their experiment used entangled electron spins in nitrogen vacancy centers in diamond, with the 2 detectors separated by 1.3 kilometers of campus, far enough that the measurement at one detector was completed before any light speed signal could reach the other. They simultaneously closed the locality loophole, the detection loophole, which arises if not all particles are detected, potentially biasing the statistics, and the freedom of choice loophole, by using random number generators based on processes that were space-like separated from the measurements. The result was again an unambiguous violation of Bell's inequality. 2 other independent groups, one in Vienna led by Anton Zeilinger and one in Boulder, Colorado, at the National Institute of Standards and Technology, published similar loophole-free results in the same year. The verdict was unanimous and emphatic: local realism is false. Entanglement is real. Einstein was wrong. The ultimate recognition of this discovery came on October 4, 2022. When the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to John Clauser, Alain Aspect, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. The Nobel Committee's announcement stated that the laureates' work had shown that quantum mechanics cannot be replaced by a theory that uses hidden variables, and that their experiments had cleared the way for new technology based upon quantum information. Zeilinger, speaking after the announcement, said that the work had revealed truths about the universe that were not just counterintuitive, they challenge our most deeply held assumptions about what reality is. Clauser, who had faced significant skepticism early in his career for pursuing what many physicists considered a settled and uninteresting question, expressed a mixture of vindication and wonder, noting that the universe had turned out to be even stranger than we thought. So what exactly is happening when 2 entangled particles display these impossible correlations? Let us be very precise about this, because it is easy to either overstate or understate what entanglement is. First, let us be clear about what entanglement is not. It is not a mechanism for sending information faster than light. Despite the word instantaneous appearing in descriptions of entanglement, you cannot use entangled particles to transmit a message from Boston to San Francisco faster than light can travel. Here is why, when you measure your photon in Boston and find it vertically polarized, you learn instantly that the photon in San Francisco is horizontally polarized. But the person in San Francisco does not know that you have measured your photon. From their perspective, when they measure their photon, they simply get a random result, horizontal or vertical with equal probability. It is only when the 2 of you compare your results later, using ordinary communication like a phone call or an email, that the correlations become apparent. The entanglement produces correlated randomness, not controllable communication. Einstein's special theory of relativity, and its prohibition on faster-than-light signaling, remains intact. What entanglement does mean, however, is something arguably even more profound. It means that the two particles do not have independent realities. Before measurement, neither photon has a definite polarization. They are not two separate objects with two separate sets of properties. They are one unified quantum system described by a single wave function, even if they are on opposite sides of the planet. The wave function does not say photon A is vertical and photon B is horizontal. It says photon A and photon B are in a superposition of a vertical be horizontal and a horizontal be vertical. The properties do not exist until measurement collapses this shared wave function. And when the collapse happens, it happens for the whole system at once. This is what makes entanglement so radically different from the glove-in-a-box analogy. With classical gloves, the left glove was always a left glove, even before you open the box. With entangled particles, there is no pre-existing answer. The polarization literally comes into existence at the moment of measurement. And yet the two results are perfectly correlated every single time. There is nothing in our everyday experience that prepares us for this. It is as if the universe has a kind of non-local wholeness, a deep interconnectedness that operates beneath the surface of what we perceive as separate objects in separate places. This has led some physicists and philosophers to ask extraordinarily provocative questions about the nature of time and causality in the quantum world. In a series of experiments involving what is called delayed choice entanglement swapping, physicists have shown that the decision of whether or not to entangle two particles can be made after those particles have already been detected. And yet the statistics of the earlier detections are affected as if the entanglement had been established before the measurements occurred. In one famous version of this experiment, conducted by Zeelinger's group in Vienna, 4 photons were generated, and the decision to project 2 of them into an entangled state was made randomly after the other 2 had already been measured and their results recorded. When the data was later sorted based on the outcomes of the delayed choice, the previously measured photons showed the signature correlations of entanglement, as if the future choice had retroactively influenced the past measurement. This does not allow genuine backwards-in-time communication. The correlations only become visible after the results are compared using ordinary forward-in-time communication, but it does raise unsettling questions about whether the past has a definite state before the future is determined. Some interpretations of quantum mechanics, such as the two-state vector formalism developed by Yakir Aharonov and colleagues, suggest that quantum events are influenced by both past and future boundary conditions, and that our usual notion of time flowing in one direction may be an approximation that breaks down at the quantum level. Now, as extraordinary as entanglement is at the level of individual particles, the truly revolutionary developments of the last decade have been the realization that entanglement may not just be a feature of the quantum world, it may be the very thing that holds the universe together. This idea emerges from one of the deepest unsolved problems in all of physics: the reconciliation of quantum mechanics with general relativity, Einstein's theory of gravity. Quantum mechanics governs the very small, atoms, electrons, photons. General relativity governs the very large, stars, galaxies, the expansion of the universe. Both theories are spectacularly successful in their respective domains, but they are mathematically incompatible with each other, and combining them has been the holy grail of theoretical physics for nearly a century. The breakthrough insight came from an unexpected direction: the study of black holes and a theoretical framework called the ADS/CFT correspondence, or holographic principle, developed by the Argentine-American theoretical physicist Juan Meldacena in 1997. The holographic principle, roughly speaking, suggests that all the information about a volume of space can be encoded on its boundary, much like a three-dimensional hologram is encoded on a two-dimensional surface. Within this framework, physicists began to notice a stunning connection between entanglement and the geometry of spacetime. In 2010, the Canadian physicist Mark van Ramsdonk at the University of British Columbia published a provocative essay arguing that quantum entanglement is the glue that holds spacetime together. Van Ramsdonk used thought experiments within the holographic framework to show that if you remove entanglement between two regions of a quantum system, the corresponding regions of spacetime pinch off and separate from each other. Conversely, increasing entanglement between two regions brings the corresponding spacetime regions closer together. Space is just a geometrical representation of the entanglement structure of the underlying quantum state, Van Ramsdonk argued. In other words, the three-dimensional space we perceive, the distance between your hand and this screen, the gap between the Earth and the Moon, the 93 billion light-year diameter of the observable universe, all of it might be emergent, arising from a vast network of quantum entanglement among more fundamental degrees of freedom that exist at a deeper level of reality. Space is not the stage on which quantum mechanics plays out. Space is what quantum mechanics builds. This idea received a powerful boost in 2013 when Mel DeSena and the American physicist Leonard Susskind of Stanford University proposed the ER equals EPR conjecture. The name itself is a kind of equation. ER refers to Einstein-Rosen bridges, which is the technical term for wormholes, hypothetical tunnels through spacetime that connect two distant regions. First described by Einstein and Rosen in a 1935 paper published, remarkably, the same year as the EPR paper on entanglement. EPR refers to Einstein-Podolsky-Rosen correlations, the entanglement phenomenon itself. The ER equals EPR conjecture states, simply and astonishingly, that these are the same thing. Every pair of entangled particles is connected by a wormhole. Every wormhole corresponds to entanglement. The spooky invisible thread that Einstein dismissed is, according to this conjecture, literally a bridge through the fabric of spacetime. If this is true, then the billions upon billions of entangled particles scattered across the universe are connected by a vast, unimaginably complex web of microscopic wormholes. And this web is what gives spacetime its structure, its connectivity, its very existence. The universe is not a collection of separate objects sitting in space. It is a single entangled quantum system, and space is the way that entanglement looks when you zoom out far enough. It is important to emphasize that ER equals EPR remains a conjecture. It has not been experimentally proven, and it may never be directly testable, since the wormholes in question are far too small and ephemeral to detect with any foreseeable technology. But it has generated enormous excitement in the theoretical physics community because it offers a potential pathway to the long-sought theory of quantum gravity. If spacetime geometry emerges from entanglement, then understanding entanglement deeply enough might allow us to derive Einstein's equations of general relativity from quantum mechanical principles, effectively unifying the two great pillars of 20th century physics. And there have been tantalizing hints that the conjecture is on the right track. In late 2022, a team of researchers from the California Institute of Technology, Harvard University, the Fermi National Accelerator Laboratory, and Google's Quantum AI division published a paper in the journal Nature describing an experiment in which they simulated a traversable wormhole on Google's Sycamore quantum processor. They used 9 qubits, quantum bits, the fundamental units of quantum computation, to create a simplified model of a quantum gravitational system described by something called the SYK model, named after Subir Suchdev, Jinwoo Yi, and Alexei Kitaev, and showed that information inserted on one side of the system emerged on the other side in a way that was consistent with the information having traversed a wormhole through an emergent spacetime. The research team described what they observed as a filament of real spacetime, formed in a different dimension than the one our quantum processor inhabits. This was not, to be clear, a real wormhole in our universe. It was a quantum simulation of a wormhole in a toy model of a universe. But it demonstrated that the mathematical relationship between entanglement and spacetime geometry can be instantiated in a real physical system and produces the expected results, which is a remarkable proof of concept for the ER equals EPR paradigm. The implications of all this for our understanding of the universe are staggering. If entanglement is the fundamental building block of spacetime, then space, time, distance, and locality, the very concepts we use to organize our experience of the world, are not fundamental aspects of reality. They are emergent properties of a deeper quantum substructure. Like the way temperature is not a fundamental property of individual molecules, but an emergent property of their collective behavior. The universe, at its most fundamental level, may have no space and no time at all, just a vast, shimmering web of quantum information and entanglement, from which the spacetime we experience arises as a kind of large-scale approximation. This is a genuinely revolutionary idea, and it is one of the most active areas of research in theoretical physics today, pursued by hundreds of physicists at institutions including Princeton, Stanford, MIT, Harvard, Caltech, the Institute for Advanced Study, and the Perimeter Institute for Theoretical Physics. But entanglement's implications extend beyond cosmology and fundamental physics into the very fabric of everyday reality, or at least, into the biology of living organisms. One of the most surprising discoveries of the last 2 decades is that quantum effects, including entanglement, may play a functional role in biological systems, a field now known as quantum biology. The most compelling example involves the navigational abilities of migratory birds. Every autumn, species like the European robin undertake journeys of thousands of miles, navigating with a precision that has puzzled biologists for centuries. Part of their navigational toolkit, it is now believed, is a quantum compass. Inside the bird's retina, there is a protein called cryptochrome. When a photon of blue light strikes a cryptochrome molecule, it triggers a chemical reaction that produces a pair of molecules called a radical pair, each carrying an unpaired electron. These 2 electrons are entangled, their spins are correlated in the quantum mechanical sense. The radical pair is exquisitely sensitive to the Earth's magnetic field, depending on the orientation of the field relative to the molecule. The 2 entangled electrons undergo slightly different chemical transformations, and these differences are amplified by the bird's visual processing system, effectively allowing the bird to see the magnetic field as a pattern of light and shadow overlaid on its visual field. Research published in journals including Nature and the Proceedings of the National Academy of Sciences has provided strong evidence for this mechanism, showing that the radical pair process in cryptochrome is sensitive enough to detect the Earth's relatively weak magnetic field, which is about 25 to 65 microteslas depending on location. If this is correct, and the evidence is increasingly compelling, then quantum entanglement is not just an abstract laboratory phenomenon. It is something that a bird uses every day to find its way across continents. It is a technology that evolution discovered billions of years before human physicists did. This naturally raises the question of whether quantum effects might also play a role in the most complex biological system we know of, the human brain. This is where we enter deeply speculative territory, and it is important to be transparent about the difference between established science and conjecture. The most prominent proposal for quantum consciousness is the orchestrated objective reduction theory, or orchestra, developed by the Nobel Prize-winning mathematical physicist Sir Roger Penrose of the University of Oxford and the anesthesiologist Stuart Hameroff of the University of Arizona. Penrose and Hameroff proposed in the mid-1990s that consciousness arises from quantum computations taking place inside structures called microtubules, which are tiny protein tubes found inside every neuron in the brain. According to their theory, quantum superpositions within microtubules undergo a special form of wave function collapse, objective reduction, that is orchestrated by biological processes. And it is this orchestrated collapse that gives rise to conscious experience. If orchestra is correct, then consciousness is fundamentally a quantum phenomenon, and the entanglement of quantum states within microtubules would be the physical basis of the unified, integrated experience we call awareness. The brain would not simply be a classical computer made of neurons firing electrical signals. It would be a quantum computer of staggering complexity, exploiting entanglement to process information in ways that no classical system could replicate. However, orchestra remains highly controversial and is not accepted by the mainstream neuroscience or physics communities. The primary objection is the problem of decoherence. Quantum superpositions and entanglement are extremely fragile and are destroyed almost instantly by thermal noise and interactions with the environment. A process called decoherence The human brain operates at approximately 98.6 degrees Fahrenheit, a warm, wet, noisy biological environment that seems profoundly hostile to delicate quantum coherence. Calculations by physicists such as Max Tegmark of MIT have suggested that quantum superpositions in microtubules would decohere in about 10 to the power of negative 13 seconds, roughly a 10 trillionth of a second, far too fast to play any functional role in neural processing, which operates on timescales of milliseconds. As the physicist Lawrence Krauss once remarked, whenever you hear the word quantum used in the context of consciousness, you should be skeptical. The brain is not a quantum mechanically closed system. Penrose and Hameroff have responded to these criticisms, arguing that biological structures might protect quantum coherence in ways not yet fully understood, and pointing to recent experiments suggesting that quantum effects can persist in warm biological systems for longer than previously thought. But the evidence remains far from conclusive, and most neuroscientists continue to favor classical explanations for consciousness based on neural network dynamics, information integration, and synaptic plasticity. Regardless of whether consciousness turns out to have quantum underpinnings, the technological applications of quantum entanglement are advancing at a breathtaking pace, and they promise to transform communication, computation, and sensing in the coming decades. Let us start with quantum communication and the phenomenon of quantum teleportation. Despite the science fiction name, quantum teleportation does not involve the transfer of matter or energy from one place to another. Instead, it is a protocol for transferring a quantum state, the complete quantum information describing a particle, from one location to another, using a combination of entanglement and classical communication. The protocol works like this: two parties, conventionally called Alice and Bob, share a pair of entangled particles. Alice has an additional particle whose quantum state she wants to transmit to Bob. Alice performs a joint measurement on her two particles, the one she wants to teleport and her half of the entangled pair, and obtains a result that she sends to Bob via a classical channel, like a phone call. Bob then performs a corresponding operation on his entangled particle based on Alice's message, and his particle is transformed into an exact replica of the original quantum state that Alice wanted to send. The original state at Alice's location is destroyed in the process, consistent with the no-cloning theorem of quantum mechanics, which prohibits the creation of identical copies of an arbitrary quantum state. The first experimental demonstration of quantum teleportation was achieved in 1997 by Anton Zielinger's group in Innsbruck, Austria, using entangled photons. Since then, the distances over which teleportation has been achieved have grown dramatically. The most spectacular milestone came from the Chinese quantum satellite program led by physicist Jianwei Pan of the University of Science and Technology of China. In August 2016, China launched the Mischius satellite, the world's first satellite dedicated entirely to quantum experiments. Named after the ancient Chinese philosopher also known as Mozi, Mischius orbits the Earth at an altitude of about 310 miles and is equipped with a sophisticated photon source that can generate pairs of entangled photons and beam them down to ground stations below. In 2017, Pan's team reported that they had used Mischius to distribute entangled photons to two ground stations separated by approximately 745 miles, and the entanglement was verified to survive the journey through the atmosphere and space. This was a factor of 10 improvement over any previous entanglement distribution experiment. The satellite-based approach was critical because sending entangled photons through optical fibers over long distances is extremely lossy. The photons get absorbed or scattered, whereas the near vacuum of space allows them to travel with much less degradation. Pan's team reported that the entanglement distribution efficiency of the satellite-to-ground link was 1 trillion times better, 12 orders of magnitude higher, than the best optical fiber technology available at the time. But the ambitions did not stop there. In subsequent experiments, Pan's team used the Mischius satellite to perform intercontinental quantum key distribution, establishing secure cryptographic keys between ground stations in China and in Austria, partnering with Zielinger's group in Vienna, with the satellite serving as a trusted relay. This demonstrated the feasibility of a global quantum communication network using satellite infrastructure. The practical significance of this is enormous. Quantum key distribution, or QKD, exploits a fundamental property of quantum mechanics, the no-cloning theorem and the disturbance caused by measurement, to create encryption keys that are guaranteed to be secure by the laws of physics. If an eavesdropper tries to intercept the entangled photons and measure them, the act of measurement inevitably disturbs the quantum states, introducing detectable errors in the key. Alice and Bob can detect these errors by comparing a subset of their results over a public channel. And if the error rate exceeds a certain threshold, they know the line has been compromised and can discard the key. Unlike classical encryption methods, which rely on mathematical problems that could, in principle, be solved by a sufficiently powerful computer, including the quantum computers currently being developed, quantum encryption is secure against any computational attack, now or in the future, because its security rests on the fundamental laws of physics rather than on computational complexity. The development of quantum networks has also taken a major step forward on the ground. In 2021, a team at the Chutech Research Center at Delft University of Technology in the Netherlands, led by Ronald Hansen and Matteo Pompili, demonstrated the world's first multi-node quantum network. The network consisted of 3 quantum nodes, whimsically named Alice, Bob, and Charlie, connected by entanglement. The nodes used qubits based on nitrogen vacancy centers and diamond, the same technology used in the 2015 loophole-free Bell test. The key achievement was demonstrating entanglement swapping through the intermediate node Bob, which allowed the end nodes Alice and Charlie to become entangled even though they had never directly interacted. This is the quantum equivalent of a network relay, and it is essential for building quantum networks that span large distances. Pompili stated in the team's announcement that a future quantum internet will enable applications that are fundamentally impossible with classical communication, such as provably secure communication, quantum cloud computing, where you can compute on encrypted data without the cloud ever learning what your data is, and ultra-precise clock synchronization across the globe. The parallel to the early days of the classical internet in the 1970s and 1980s is apt. Just as ARPANET, a modest network connecting a handful of university computers, eventually evolved into the global internet that transformed civilization. These small-scale quantum networks are the embryonic precursors of a quantum internet that could fundamentally change how information is processed, transmitted, and secured. Meanwhile, researchers have been pushing the boundaries of what quantum teleportation can achieve in terms of information capacity. In 2023, an international team from South Africa, Germany, and Spain, led by Andrew Forbes of the University of the Witwatersrand in Johannesburg, demonstrated the quantum teleportation of high-dimensional quantum states using just 2 entangled photons. Previous teleportation experiments were limited to qubits, 2-dimensional quantum states, essentially quantum zeros and ones. But Forbes's team showed that by exploiting the orbital angular momentum of photons, essentially the spatial pattern of the light wave, they could teleport much richer quantum states, encoding the equivalent of entire images in a single photon's spatial structure. They demonstrated the teleportation of alphabet characters and simple images, with the information being reconstructed at the receiving end without any physical transmission of the photon carrying that information. Forbes described the achievement in vivid terms. Previously, even in quantum communication, one had to physically send information from one point to another. Now we have shown that information can be teleported. It does not traverse the physical connection at all. The technology of Star Trek has become the technology of the laboratory. This advance is significant because high-dimensional quantum states can carry exponentially more information than simple qubits, and teleporting them is essential for building quantum networks that can handle the data rates needed for practical applications. Quantum computing is another domain being revolutionized by entanglement. A quantum computer derives its power from the ability to manipulate qubits that are in superposition and, crucially, entangled with each other, while a classical computer processes bits that are either 0 or 1. A quantum computer processes qubits that can be in a superposition of 0 and 1 simultaneously. And when multiple qubits are entangled, the system can explore a vast number of computational pathways in parallel. For certain types of problems, factoring large numbers, simulating molecular interactions, optimizing complex systems, quantum computers are expected to be exponentially faster than any classical machine. As of early 2025, the most advanced quantum processors include IBM's Heron chips with over 1,000 qubits, Google's Sycamore and Willow processors, which have demonstrated quantum error correction milestones, and systems from companies like Quantinuum, which in collaboration with Microsoft achieved high-fidelity entanglement of 12 logical qubits in 2024. These are still early days. Current quantum computers are noisy and error-prone, and practical quantum advantage for real-world problems has not yet been definitively demonstrated, but the trajectory is clear, and the investment is staggering, with governments and corporations worldwide pouring tens of billions of dollars into quantum technology development. Quantum sensing is yet another frontier where entanglement is proving transformative. Quantum sensors exploit the extreme sensitivity of entangled quantum states to external perturbations, magnetic fields, gravitational fields, accelerations, temperature changes, to achieve measurement precisions that are fundamentally impossible with classical instruments. The Laser Interferometer Gravitational Wave Observatory, or LIGO, which detected gravitational waves for the first time in September 2015, already uses quantum techniques, specifically squeezed light, which exploits quantum correlations between photons to reduce measurement noise below the standard quantum limit. Future generations of gravitational wave detectors are expected to make even greater use of entanglement to push sensitivity to extraordinary levels. In medicine, quantum magnetometers based on nitrogen vacancy centers and diamond and other platforms are being developed for magnetoencephalography, brain imaging that maps the faint magnetic fields produced by neural activity, with sensitivity and spatial resolution far beyond current clinical instruments. In navigation, quantum accelerometers and gyroscopes could provide GPS-independent positioning systems for submarines, spacecraft, and autonomous vehicles, using the quantum properties of ultra-cold atoms to measure motion with exquisite precision. So where does all of this leave us? Let us take a step back and consider the full sweep of what quantum entanglement has revealed about the nature of reality. We began with a simple observation: two particles, prepared together and then separated, display correlations that cannot be explained by any local deterministic theory. This observation, confirmed by decades of rigorous experiments and honored with the 2022 Nobel Prize, tells us something deep and unsettling about the universe. It is not locally real, in the technical sense that physicists use those words. The properties of distant objects are not independent of each other, and they are not determined until they are measured. The universe does not consist of separate, independent pieces interacting through local signals. It is, at the quantum level, a single interconnected whole. From this foundation, we have followed the thread to extraordinary places. We have seen how entanglement may be the fundamental building block of spacetime itself, stitching together the fabric of the cosmos through a web of microscopic wormholes. We have seen how living organisms, birds navigating across continents, may exploit entanglement as a biological compass. We have seen how entanglement enables quantum teleportation, quantum cryptography, quantum computing, and quantum sensing, technologies that are already transitioning from laboratory curiosities to practical tools that will reshape communication, computation, medicine, and national security in the coming decades. And we have glimpsed the tantalizing but unproven possibility that entanglement might play a role in the most mysterious phenomenon of all, consciousness itself. Einstein once wrote, in a letter of condolence to the family of his lifelong friend Michel Besso, who passed away just weeks before Einstein himself in 1955. Now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. Einstein was speaking of time, but his words resonate with what entanglement has revealed about separation in general. The distinction between here and there, between this particle and that particle, between one thing and another, quantum mechanics tells us that these distinctions, too, are not as fundamental as they appear. At the deepest level of reality, everything is connected. The invisible threads are real. They bind particle to particle, place to place, and perhaps even mind to cosmos, in ways we are only beginning to understand. The old intuition that we are somehow part of the universe, that the boundary between self and cosmos is more permeable than it seems, that intuition, which poets and mystics have expressed for millennia, turns out to have a rigorous scientific foundation, one built on Bell's theorem, verified by aspects experiments, and celebrated by the highest honors the scientific community can bestow. The universe, it turns out, is not a collection of separate things. It is one thing, seen from many angles. And the thread that connects it all, the quantum thread, the invisible thread, the thread that Einstein called spooky and Schrödinger called the characteristic trait of quantum mechanics, that thread is entanglement. We are only beginning to pull on it, and already, the tapestry that is unraveling is more beautiful, more strange, and more interconnected than anything we ever imagined. The journey into the quantum world is far from over. In many ways, it has only just begun. And the most astonishing revelations about the nature of space, time, reality, and perhaps even consciousness may still lie ahead, woven into the fabric of a universe that refuses to be divided, that insists on its own profound and spooky unity, and that invites us, with every new discovery, to see ourselves not as isolated specks adrift in an indifferent void, but as entangled threads in a single, magnificent, endlessly surprising cosmic tapestry.